Hello everyone, my name is Arash Khatibi and today I'm going to give you a short tutorial about a simulation software which is really well known in designing and simulation of renewable energy systems especially, and you can say also in general for all energy systems like the normal grids or all the also the conventional energy systems. And this program is called HOMER, and this version that I'm going to show you is HOMER Pro microgrid analysis tool. It is written also above this window, and this is the version 3.13, I guess. Yeah, no, I'm sure that this is the latest version of this software. And as you've also seen in the lecture slides, you can also download this program freely from their website homerenergy.com. You can download it freely, and you can register your account with an email address, and it will work for 3 weeks just completely freely as a trial version, and all the components are also available in the trial version. So I'm going to ask you to download this software for sure and try it at home, and then try to play with it a bit at home, and then just make yourself familiar with it, which is really interesting and gives you a great idea of how to design and simulate energy systems. So as I said, the trial version is free for 3 weeks, and then afterwards you need to pay for the software. But of course, it's a really expensive software. You don't need to buy it, of course, but try to make yourself familiar in the trial version. Okay, so as I said, this Homer Energy company has different softwares as well, but we are going to talk about Homer Pro. Yeah, and this is the first page of the software when it is opened. You may see here that we have a toolbar here, of course. We have some comment area about this, that the program gives you some proposal or suggestions on how to improve your project, for example. And then we have the main area of the project, and then here is the map of the world. So you can search for the location, for example, that your project is going to be installed or your system is going to be installed, or you can give the geographical coordinates of the location in this area, and then it will find it for you. Or as I said, yeah, you can also scroll into the map like what I'm doing right now, and then find your place and just choose that location. So this is the first step, for example, in this part. Yeah, and then for example, here is the area that you can put a name for your project, and then the author of the project, and you can also write some description of the project. And there are some basic parameters in the beginning that you can add, like the discount rate or inflation rate of the installation country, for example. And afterwards, for example, the another parameter, annual capacity shortage in percentage. It this parameter is defined like the how many percentage of electricity can be shorted in during a year. So it means that you say that, okay, I want to have a renewable energy system with only, for example, photovoltaic modules, and I am allowed to have 10 percentage of shortage, for example, during the whole year, which is a really high number, but just as an example. Or usually you say that, okay, I don't want any capacity shortage, so this number should stay at 0%. And And then another parameter is the project lifetime, which you say that, okay, my project is going to work for 25 years. And then it shows you the financial and all the other costs of the project during this lifetime. So, as I said, yeah, there's a toolbar here. You can find the first tab is home, which wherever we are, it brings us back to this page. So for example, if I'm in the result page, home will just guide me through the first page one more time. Design page is showing the design of the our system, but so far we don't have any implemented system already, so there's nothing else here. Results page, of course, will guide us to the results page after running the simulation. And then there is this library that goes into the library of HOMER Pro software, which is needed sometimes when we are talking about different definitions or parameters, or maybe we want to know more about how a calculation is being done in the background. So it just shows us some formulas about it and then said that, okay, the program is calculating that parameter through these calculations. And later you see also various toolbars here, like load, components, resources, project, and help. Yeah, now first I'm going to start talking about the load. In load tab, you can see electric load number 1, electric load number 2, and a deferrable load. These other components which are blanked out, it means that they are not available in this version that I am having on my computer. But when you have the trial version, as I said, all the components will be available for you for 3 weeks. And then depending on what version you will buy afterwards, some of these components will be available and some will be not available. Like for example, let me just go to the components tab, and you see that some boiler, hydro energy, and electrolyzer or something, they are not available in this version that I have. But the most of the components that we need for renewable energy systems is available, and I'm going to show you about those. Okay, so I was talking about the load, and then the first one is electric load number 1. We can add more than one, like electric load number 2. We can even add much more, and then we also can have a deferrable load, which means that we can edit the load however that we as the user want. Okay, so this is the page for electric load number 1. Yeah, this part is about the introduction of the other softwares of the HOMER energy company. Yeah, or you can say that it's just the advertisement sometimes. And yeah, okay, so the first part that we are going to see is this rectangle here. There are some default loads or default load profiles which are already implemented in HOMER, and if you want to just run a quick and just short simulation, we can just choose one of them. It's easy, it is already, as I said, implemented. All the numbers are already inside, and then we don't need to enter any load amount into the program first. So for example, in the first one, we can say that, okay, yeah, which month is the peak month of the load during the year. So usually with countries in northern hemisphere, the load profile will be much higher in January. It means that the demand is much higher in January or in winter time. And then for the countries which are in the southern hemisphere, their load demand is also higher at their winter times, which is our summer times, for example, in Germany, which is July. So I'm going to just choose January for Germany that we are looking at it now. And then I'm going to choose one residential load. We can also choose commercial, industrial, community, or a blank load, which we can enter all the load amounts on our own. I'm just choosing residential right now, and then I will click on OK. So now the page is changed to this page with different diagrams. Okay, so at start we can say that we can edit the name of this electric load. We can just consider it as a, I don't know, house number 1 or factory number 1 or something like that, or even just a small load like, for example, the refrigerator, and then we put the numbers for usage of a refrigerator during the day. So this is the hourly distribution of the load. For example, for this residential load that is entered by default in HOMER, you can say that, okay, in January, in the hours from midnight to 11 o'clock at night, these are the different various numbers of the load in kilowatt. So if you take a look at the numbers, you can see that, okay, it's starting from a slightly low number around 100 watt, and then it goes higher in the beginning of the morning, and then it goes a bit lower, and then around 11, 12 o'clock until, yeah, you can say 13 o'clock, which is high demand around these hours, and then afterwards it goes down again, and also again in the evening it goes higher to the maximum number of around 790, or no, sorry, this one is also begin, so around 1477 watt or 1.4 kilowatt, and then again it goes back to the minimum number of the day. So these numbers are drawn here in this diagram. So the horizontal axis is about the hours of a day, and then the vertical one is the amount of load in watt or kilowatt here. So these are the numbers exactly. The first one is 130, and then 110, and then it goes higher, as I said, in the beginning of the day, and then it goes down again, and then also in the middle of the day it goes again high a bit, and then goes down, and then as we expect in the evening, which is the most demanding time, we have the maximum load here. Okay, so now if I click on this button, show all month, I can also see the details for every hour of the whole year. Like, for example, in January, they can say that in all days this is the load profile. So in all days in January at 9 o'clock we have 500 watt of demand, like this. It's just simplified like that. And also in February, all days of February, but it is a different number than January, and you can see and just take a look at it until December, and you can also edit each of them if you want, and you can also copy these numbers to the right and to the left, or like weekends or something like this. You can, as I said, even change the load demand in weekends and weekdays, and even just make it different for every month. So if you play more with the software, you can also find ways to add exactly hourly load profiles into the programs, and then not consider all the January days as they have the same load profile. You can also change them for every single day, but in this case we don't need to do that. We are just looking at an example here. So okay, that was the electric load, and then with this button, show all months, you can check all the load profiles in the months, in different months of the year. So, and then you can see a seasonal profile of it, yeah, with these kind of diagram which shows the median, maximum, minimum, and then also the average of the load in different months of the year. And this one is the yearly profile of the our electric load, which shows you this, like this is the first day of the year, and then the final number on the horizontal axis is the last day of the year or final day of the year, and the vertical axis is also the hours of the day from 0 to 24. You can take a look at all the numbers and all the dates and all the hours in this diagram. So you see that, okay, the beginning of this, when we go vertically on this diagram, the beginning of the beginning hours of the day is during the midnight, and then of course it goes to middle of the day, and then it goes to evening. So as we expect, around 6 o'clock in the evening until 8 o'clock or 9 o'clock is the maximum demand for the electricity. And then you can see that also in the middle of the day it's also a bit higher, and also in the beginning of the day. But in between, the colors are dark blue, which are less than 500 watt, for example. Okay, so as I said, if I keep my mouse here at this point, it means that it shows that it is 25th of July and 2007, which is like an example. I guess this load was taken from a specific date, and then it also shows the value of that load, which is, for example, in this point it is 660 watt. Okay, so here we have also some parameters, which is the average of the load in kilowatt hours per day, which for this residential load, which is around 11.25 kilowatt hours per day, and the average load is during the whole year is 0.47 kilowatt or 470 watt. The peak was this number. I don't know, it happened maybe around these points in red in this diagram, or also here. And yeah, we have also another parameter like load factor, but we don't care about it right now. And if you want to add an efficiency to the for example, our load, you can also add it here. If you want to say that, okay, we have also this amount of loss, energy loss with this load, you can also add it with this point. And then with clicking on this button plot, you can take a look at various diagrams of the load. Yeah, you can add different diagrams here, and then you can take a look at them. But let's go to monthly. As I said, this is the monthly, which we've seen already here. And then we go to the profile. So this is how our load profile looks for every single month of the year. So January is looking like this, and then, for example, in November is a bit higher in this amount, or it doesn't look that way, but at least it's a sharp peak here. And in the summer times, where is it? Yeah, like August or July, you can see the numbers are a bit lower. And yeah, that's it. So you can, as I said, take a look at the diagrams for each month as well. If you go to DMAP, you can just follow the numbers again, like what we had here for the yearly profile. And then you can also take a look at the histogram diagram of it, and then like the horizontal axis is the scale data in kilowatt, and then the frequency is on vertical axis. So you can say that the load demand of a bit less than 500 watt is the highest or the most frequent load demand, which is around 17%. And and then okay, so that was for the load. Other parts you can also play with the software yourselves and then find more about those. So I'm going to show you the next part in components, the next toolbar, so which is components, and then you can add or edit or modify different components of the project to the system from this point. You can add a controller, you can add a generator like diesel generator or all conventional generators to the system. You can add a photovoltaic module or a photovoltaic module systems with all strings and whatever. And then you can also add wind turbines and then storage systems with different type of storage like battery and other types of the batteries, or a storage system like flywheels. Sorry, let me just take a look at this part later. And then you can also add a converter or inverter to the system, and if you want, at the end you can add a grid to the system, which this version that I have. As I said, some other components like hydrogen tank or electrolyzer is not available in this version, but we also don't need to talk about them right now. Okay, so let's click on generator and then show what's happening here. So you can choose some options for a generator from this tab, and then you can see that generic 10 kilowatt fixed capacity generator set, or generic 50 kilowatt. It means that these generators, they are not specifically defined like with a brand and with a model. It's just generic ones with a capacity. And then you can see also that here, for example, fuel cell is also available here. But if you want to choose one generator with its specific brand and model, you can click on this complete catalog button, and then you can find many available generators in this area. You can also take a look at the manufacturer parts. For example, in this case it's Caterpillar in some of them, and then GE, General Electric, and then a lot of other manufacturers. But you can also add whatever that you want in between. You can also define a generator on your own as well. Okay, so I'm just going to click on, for example, a generic 50 kilowatt generator, and then I'm going to click on add generator. So now this will be added, and then I can see the other parameters of the generator here. So here you can see the different characteristics of the generator. This is a diesel generator with the capacity of 50 kilowatt and fuel curve intercept of 1.65 liters of fuel per hour, and fuel curve slope of 273 liters per hour per kilowatt. You can also take a look at the emission amounts of this generator here, and then the fuel properties and whatever that is written. So you can also, in this area, you can add the price, the buying price of this generator first, and then you can also add the replacement cost of it. So for example, after 10 years you want to change it, so if you need to pay the exact same amount, or no, you need to consider more. And operation and maintenance of the device can also be added here, and the unit for it is already in dollar per operating hour, and for example in this one is $1.50 for 1 hour of operation. And then you can also add the fuel price, in this case the diesel price, to the system with the unit of dollar per liter, which is now already is by default on $1. So yeah, what else I can show you here? The other ones is just the normal stuff. You can choose that if this generator is producing in AC or in DC. So let's see if it is on AC. Let's take a look at this schematic diagram here, which is generator is connected to our AC bus bar, which is connected to our electric load, which is also an AC load. But if I choose DC here, it shows that generator is providing to a DC line, and then our load is also AC, so we need to think about some inverter or converter in between. But as I said, if I click on AC and keep it that way, so there's no need for a converter. Yeah, so yeah, there's also one option here that you can say that I want to simulate systems with and without this generator. So if we say that I have a PV generator as well, so you also want to take a look at the systems without this generator, or you want to say that, okay, I want to know that all our systems, all other scenarios also include some generator. So you need to click on this one, and then yeah, choose the right option. Yeah, you can also keep on clicking advanced here, advanced button here, and it goes to much more options here, but I don't want to talk about too long for this part. So let's go to the next one, which is the PV generator. So I'm going to just keep this generator, for example, until later, and then I'm going to click on PV. So yeah, this is the exact same idea as generator. You can choose the main type of the generator or photovoltaic modules, like generic flat plate PV, concentrating PV, or another type, variotrack, for example. But yeah, generic flat plate PV is what we need right now. As I said, you can also click on complete catalog here, and then take a look at different manufacturers and choose one of those companies like Schneider Electric, SMA, Sharp. Yeah, there are many known companies. Huawei, sometimes QCell, which is a very well-known company for producing solar panels. So you can also choose one of those, or just consider a generic one. If you click and then choose this generic flat plate PV, after the simulation, the program will suggest you only the capacity of the PV needed for the system, and it doesn't suggest you any brand or any photovoltaic modules with good or bad efficiencies or whatever. It just shows the capacity that you need. So I'm going to click on add PV, so you can see again a new page is opening up, and then you can see that the capital cost of it is, for example, $2,500 for every kilowatt. You can change this number. You can say that, okay, I want modules which are, I don't know, $200, for example, for 200 watt or something like that, and then choose it accordingly. And then if you want to change it after its lifetime, you need to click on this area and then put the cost for replacement and the operation and maintenance costs, and then also the lifetime of it. You can say that 25 years. I'm sure that my PV is working fine. And also you can change the derating factor of the PV modules. It means that if the capacity, if the output of the module is 80% of its nominal capacity, so it is considered as a derated PV module, and then you need to replace it. So yeah, you can also choose AC or DC electrical bus here, but yeah, we just keep it on DC. Of course, the PV modules are producing DC. So yeah, let's see if I click on advanced. Yeah, there are some other parameters that I can enter, like model a maximum power point tracker as well in between. I can say that, okay, yes, model an MPPT with a lifetime of 15 years and the size of it. And I also can choose an efficiency table for the maximum PowerPoint tracker. For example, by default is 95%, but okay, let's put it out for now. Then the orientation of our PV module. Yeah, ground reflectance of the area, you need to know it um, based on the location that you're going to install the PV modules. For example, by default is 20%. It meaning the same as the albedo amount. And you can also choose the tracking system if you have any for this PV module. You can say that, okay, I want to track it on a horizontal axis and I want to adjust it monthly, weekly, or daily, or vertical axis even, and then also in 2 axis if you want. Yeah, there are 2 ticks here. You can just check one of these check marks or even both of them. The first one is about use default slope. So depending on the location, HOMER suggests you panel slope, and then you can keep that as well, or if you're obliged to keep, for example, a slope for your PV modules, you can also choose here and then say that, okay, I want to have it in 30 degrees, for example. And also the azimuth. Again, default azimuth means that the HOMER energy software will suggest you the default azimuth, or you can say that no, I want to install my photovoltaic modules only to the south or to the north or something like that, and then you need to enter the azimuth angle here. Next one is the temperature. If you want to consider temperature effects, yeah, you just click it on, and then you can say that, okay, I want to have temperature effects on power with this percentage per centigrade, which is, for example, in this case by default is minus 0.5% per Celsius. And you also need to enter nominal operating cell temperature of the module, and if you want, you can also add the efficiency of the module here or even change it. And of course the efficiency must be in STC or standard test conditions. So yeah, that was for it for this part. So I'm going to go to the next component. Next one is the wind turbine. Yeah, this is exactly the same explanations. You can choose the generic ones here and more specific ones here with different brands like Enercon, yeah, other ones. And I'm going to keep this generic wind turbine with 3 kilowatt of nominal output. So when you add it, you can see again different parameters which we can decide on our own, like the capital cost of it, replacement cost, operation and maintenance cost, and then the lifetime of it, which is by default 20 years, but we can change it, of course, and the hub height. We can also say that we just change it to another height. Now by default it is set on 17 meters, and you can also say that I want to consider ambient temperature effects or not on this wind turbine. Yeah, if I click on advanced, I can see that I have a power curve for this generic wind turbine. This is the power curve. It means that it shows the power output of this type of turbine depending on the wind speed of that location, or at the same, in what specific hour. And then you can see another tab here as turbine losses. You can enter other losses here if you want, and like a maintenance table if you want. You can say that I want to do some maintenance every year or every 6 months or whatever that you want, and then the program will simulate your system based on that schedule. And then it shows also the costs. It also considers the cost of operation and maintenance for that matter. Okay, the next part I'm going to show you the storage. Again, exactly the explanation is the same. You can choose the generic battery systems. For example, this first one is lithium ion, the second one is lead acid. You can also have take a look at other storage systems like flywheels and yeah, different types. And then if you click on complete catalog, you can see a lot of battery systems or other type of storage systems. Okay, so like flywheel, for example, here. Yeah, I'm going to keep my selection on generic 1 kilowatt hours lead acid battery. Yeah, lead acid batteries are, the standard in renewable energy systems, considering PV energy especially. And but you can of course consider lithium ions, which have their own advantages and also disadvantages. Okay, so I have added one lead acid battery. You can again enter the capital cost, replacement cost, operation and maintenance, lifetime of it. This is 10 years, for example, for now. And if you want to say that, okay, my system is going to be 12 volts, so you need to just say one string. If you add two strings, it will be changed to 24 volts. You can even choose your system voltage here. Initial state of charge is 100%, which means that when we buy this battery or when we want to start our simulation, we consider this battery as fully charged. And minimum state of charge is another part that you can say that I want to keep the depth of discharge of this battery to around maximum 60%, which means that the battery will be only discharged until 40% of energy is still remaining in that battery. And it is, of course, important for the health of the battery. Okay, so yeah, that was for the storage system. Next part is the converter. If I want to add a converter as a component of the system, I can also add it here. For example, as I said, we can see that our load is in AC. Yeah, wind turbines produce also in AC, generator is in AC, but photovoltaic and our battery, of course, they are in DC, so we need a converter in between. So I will click on converter, and then you can see that the converter is added between DC and AC bus. Yeah, I can even again change the costs for the converter here, and their lifetime as well, and also the efficiency. Uh, for example, the efficiency of the inverter could be changed here. It's 95% by default. Also the rectifier, which is other way around. I mean, it is AC to DC, so that's also can be implemented here, the efficiency of this rectifier as well. Okay, so this was about the converter. Now I'm going to continue to grid here, hydrokinetic energy. We don't want to go inside that right now, just for our example. Let's go to grid. Yeah, if we want to say that our system is on grid and it's not off grid, it is connected to the grid, and then if we lack enough renewable energy, we can have it from our grid, or even if we have extra energy, extra produced energy from our renewable ones, we want to sell it back to the grid, so we need to add this component from this toolbar. So you can say that, yeah, grid power price is, for example, 10 cents per kilowatt hours, and the sellback price is 5 cents. It means that if we need more energy from the grid, we need to buy it for 10 cents, and if we want to sell our extra energy to the grid, we will be paid only 5 cents per kilowatt hours. These are the numbers that can be modified for depending to the location site and the regulations of the country. And about the net metering, we can also choose this part. You know that we have feed-in tariffs and net metering. Net metering systems, they have only one electricity counter, which considers the production and extra needed energy from the grid, and then it just gives you the result, the final result of energy which is produced and is fed to the grid, or it is bought from the grid. But if we consider feed-in tariffs, in feed-in tariffs we have two counters, electricity counters, and then these two counters, they count the amount of energy which is taken from the grid, and the other one is counting the amount of electricity which is fed to the grid from our renewable system. But this is depending on the locations. So let's just leave it like that. Okay, next tab is about the resources. I'm going to click on the resources. So I can enter my resources data in these area. Like I want to say that I have this amount of potential solar energy in this area, how much is the average irradiance level for each month, or how much is the wind speed during the whole year, or how much are the average temperature of the of this location through the whole year. So these are the basic data that we need to start designing our system based on them. So yeah, but these are of course depending on the location of the installation site. So for example, I need to go back to home for this matter right now. I'm going to click on home. Now the location, installation location is clicked on middle of the ocean here. But let's, for example, choose some place in Germany. I can, as I said, type the name of Paderborn here as an example, or enter its coordinates, and then I'm going to click on location search. So now Paderborn is chosen here in between, and it's a location, it's a default location of Paderborn in the middle of the city. But yeah, you can also take a look at the address here and the exact latitude and longitude of the location. So now that the location is set correctly as what we want, let's go back to resources and then solar GHI, for example, global horizontal irradiance. So far there is nothing, no data is downloaded here. I need to click on this button, download from internet, and the data is downloaded. It means that this data is downloaded right now from HOMER server, HOMER energy server, and this is exactly for our location, which is in Paderborn. Okay, so this is global horizontal irradiance, average global horizontal irradiance, the amount of daily radiation in kilowatt hours per square meter per day. And for example, in January, this number is around 810 watt hours per square meter. And it goes higher, of course, as what we expect in summer, and then it goes down again in winter time. You can also see the amount of the exact amounts here in this table. You can change them as you want if you want, but this data is downloaded from, as I said, the server of HOMER Pro, and they also took this data from NASA Surface Meteorology and Solar Energy Database. And this, for example, specific data, global horizontal radiation, is monthly average values over 22-year period. So these are the average numbers of daily radiation data between 1983 and 2005. So it's over 22 years. So you can consider them as a good basic data. And you can also take a look at the latitude and longitude for the location that this data is taken from. Okay. Yeah, of course, in the middle of the city or at this location, 51.5 latitude and 8.5 longitude, there is no weather station, but of course, NASA and other organizations access to can access the meteorological parameters with their satellites or other methods. So, as I said, this data is taken from what NASA satellites are measuring for this point, and of course, they are not 100% correct. But if we consider them as a whole period of 22 years, yeah, you can say that okay, this data is a correct one. It's a good one. It's a good estimation for the whole period. Okay, then I'm going to go to the next resource tab, solar DNI, direct normal irradiance data, which this part cannot be downloaded because there are no data sets for all data points on the globe. You can, if you have for your location, if you have any data, if you have taken the meteorological data for over a long period and you have the data on your own, you can import them here and then use it. But if not, you need to consider only solar GHI. Next one is wind parameter, wind energy, and the main parameter to consider the potential of wind energy is wind speed. So again, for this location, which is chosen in Paderborn, I'm going to click on wind here, download from internet, and then this is what is downloaded. It's this time it is again the data is downloaded from NASA again, but wind speed is these numbers are at 50 meters above the surface of the Earth, and their monthly average values over 10-year period. So they could be not as precise as solar GHI, which is taken for more than 22 years, but still 10 years is also not a bad number. It's long enough. And yeah, you can see that in the January we have the average wind speed of 6.78 meters per second, and then in February it's a bit lower, in March is higher, and during the summer it goes a bit lower, and then during the winter time it goes again back high. So we can say that I want to have you can change the anemometer height here, but I guess this change doesn't make any difference in the data right now. So let's go to variation with height. You can also take a look at the variation of wind speed with height, and then you can also say that okay, I want to calculate this variation with the logarithmic formula or the power law, which are two methods to calculate wind speed based on wind speed in another height. So the next one is the advanced parameter. You can say you can also add viable K parameter here, and the other parameters which are important for wind energy assessment. And then next resource is the temperature data, again based on the location that we've chosen already. So I'm going to click on download from internet, and it is downloaded immediately. Again, this is average for over 22 years for Paderborn, and then these numbers are the average daily temperature and the average amounts depending on the month of the year. So of course in January and winter times it's really low. The average value is around 1 degree Celsius, and then in summertime the average temperature goes to around 18.35, for example, in August. Yeah, so these are the basic data that we need to run our simulation. And yeah, so that was for the part of the introduction of the system. There are just some small explanation in the project tab. If I click on economics, I can, as I said, for my project, I can change the economics parameters as well, like nominal discount rate, if there is any for any country, or the expected inflation rate for example, it is various for different countries, and then you, depending on the location site, you can also change these. Project lifetime you can change, and if you have some fixed capital cost or fixed operation and maintenance, and even if you want to change the currency of the costs, for example, I'm going to change it now to euros. Let me see, yeah, like that. And then if I go to the next tab, constraints, yeah, you can see that if you have any annual capacity shortage constraints, you can also add it here. If you want to have a dedication, a fixed dedication of renewable energy into your system, you can also add it here in this minimum renewable fraction. You can say that, okay, 10% or 50%. It means that I am obliged to produce my energy, about 50% of my energy I am obliged to have it through renewable sources. So you can also choose this. And yeah, the other ones are not so important for now. Let's go to emissions. Yeah, so for example, if you have a generator here, a diesel generator here in this system that we so far implemented, and if we produce or if we emit carbon dioxide or carbon monoxide or other harmful gases or other emissions, if we have something in our system, and then if we are obliged to pay penalties for them, yeah, in per ton of this emission, so we can also add the cost for it, for this penalty. For example, if I produce 2 tons of carbon dioxide, for example, in this system, just consider it as an example. It's not that correct, but I need to pay for each ton of it, for example, I don't know, 1,000 euros. Okay, so you can also add these numbers here as well. So this was the introduction of the software so far. And as I said, of course you can play with all the areas in this software and then find more about that, and then maybe you can find other interesting stuff as well. So next part, I'm going to solve the tutorial number 6, which is already solved in your tutorial sessions with Professor Krauter. And I'm going to implement and simulate the exact example in HOMER Pro, and then see about the results, and then just compare them with what you have achieved already. So I'm going to pause the video right now, and then I will bring the tutorial question one more time in front, and then I will start implementing that. Okay, so I have found the tutorial. This is exercise 8. Sorry, I guess I told you exercise number 6, but okay, there was exercise number 6, but now it's with HOMER, so it has a new number. I hope that you can see this page as well. If this software that I'm recording with is doing his work properly, I guess it should be working. But if not, you can take a look at slide number 435, which you can find this exercise, and then I'm trying to simulate this exercise into HOMER. So the question says, an off-grid household in Rio de Janeiro with daily irradiance at worst months of the year at around this number, 4 kilowatt hours per square meter per day, has the following electrical energy needs. One ventilator of 60 watt operating from 9:30 a.m. until 11 p.m. 5 lights of 60 watt each operating from 7 p.m. until 11 p.m. One notebook computer of 30 watt operating from 6 p.m. until 9 p.m. One TV set of 100 watt operating from 8 p.m. until 10:30 p.m. Okay, so calculate the load respectively daily consumption to be supplied after energy saving measures. In the next part, the lamps will be replaced by LED lights, and then calculate the battery size with a 24 volt system, battery cycle efficiency of 80%, efficiency of charge controller equal to 95%, and inverter efficiency of 90%. And then calculate the panel size with PV conversion efficiency inclusive PR, performance ratio losses, is about around 10%. And we need to calculate the costs afterward, which in case PV panels costs €1 per watt peak for lifetime of 25 years, battery for €300 per kilowatt hours for lifetime of 4 years, and mounting and support structures of 50 cents per watt peak. And then the second part says that 5 lights of 60 watt each operating from 7 p.m. until 11 p.m. 5 LED lights of 8 watt each have the same luminance. So we want to see how much is the difference in energy that we need to provide first for conventional lamps and for in case of LED lamps. Okay. So now I'm going to start the simulation in HOMER. Okay, so this is completely a new project in HOMER. First of all, I need to enter the input data that I have from this exercise, and then run the program to see what happens with the results. Okay, so an off-grid household. First of all, an off-grid, it means that it is not connected to a grid. So that means we don't have any grid connected. This component we don't need to add it. And in Rio de Janeiro, so first of all I need to look for this location. Since there is no specific longitude and latitude, I'm going to look for Rio de Janeiro with searching it easily, and then when I zoom into the map, I can see that, yeah, of course it is in Brazil, and then Rio de Janeiro. Okay, it is already chosen. Usually the HOMER just finds the location in the middle of the city maybe, but this is the address, and this is the latitude and longitude of the location. So I'm going to also add a name for this simulation, exercise 8. And there's no description, discount rate, inflation rate, we just keep them as default. Annual capacity shortage, we just keep it as 0%. And project lifetime of 25 years as default. It's good enough. So first of all, we need to, okay. In the question says that daily irradiance at worst months of the year in Rio de Janeiro is 4 kilowatt hours per square meter per day. I don't want to implement and enter exactly this number. We're going to choose what happens exactly with the NASA data. So I'm going to just go inside the resources and then click on solar GHI, global horizontal irradiance, and then since I have chosen already my location, so I only need to click on download from internet, and this is the um, exactly global horizontal irradiance profile through the whole year, which is average over 22 years between 1983 and 2005. So the question says the worst month of the year has 4 kilowatt hours per square meter per day, but here we can see that 3.66, 3.65 and 3.66. So the minimum number here in worst months of the year, which is May, June and July, since they are in the southern hemisphere, it is 3.65 kilowatt hours per square meter per day. It's close enough to what we have in the exercise, but let's continue with this number, with this new number. So then I need to add a load for my project. You can also see the suggestions here from the software. The software suggests to add a renewable energy source, okay, but which is with the green sign, it means that it is not a must. We can add or we can go with conventional energy sources, but we need to at least enter or add a power source. This is with sign with the red sign, so it means that it's a must, and also there has to be a load for this simulation to work. So I'm going to enter a load. So I'm going to go to the load tab and then click on electric load number 1. I'm going to click choose July as for the peak month of the year, because Rio de Janeiro is in southern hemisphere, and then I'm going to click on a blank profile, which is completely free for us, so we can add our load on whatever we want. These peak months, it doesn't work right now since we are going to enter some load for the whole year, so it doesn't change it through the whole year, summer and winter time, but it was more correct to choose July. Okay, so this is the load profile, which is completely empty now. I'm going to click on show all months here. I'm going to enter the load which is written in the exercise into these hours of the day, and then copy it for all months and all weekends. These two check marks must be checked already, which says that if I enter one number here, it will be copied to all the cells to the right, and then also it will be copied to the weekends. So only in this case that we have a uniform load through the whole year, we need to mark these two check marks. Okay, so first of all, one ventilator of 60 watt operating from 9:30 a.m. until 11 p.m. Okay, so here there is no 9:30. I cannot enter 9:30, so I'm going to choose just, for example, 10 a.m. So starting from 10 a.m. I have to add 60 watt. So since here we can see that the unit is in kilowatts, so I need to enter it as kilowatts, so it is 0.06, and that is 60 watt. Okay, so from 9 or 10 a.m. until 11 p.m. So I'm going to copy this number and then add it to 11 o'clock, then add it to 12 o'clock, 13, 2 p.m., then 3 p.m., then 4 p.m., and I will continue until I reach until 11 p.m. Okay, so now all the load values between 10 a.m. and 11 p.m. are equal to 60 watts. So if I click on OK, so this will be our load so far for um, a day in the whole year. Okay, so but I still need to edit the load. The second types of load is 5 lights of 60 watt, each operating from 7 p.m. until 11 p.m. So 5 lights of 60 watt means 300 watts, 0.3 kilowatt, and then from 7 p.m. to 11 p.m. Okay, so I'm going to add from 7 p.m. here. These cells from 19 to 23 must be added with 0.3. Okay, so it is 0.360 or 360 watt, and then I'm going to copy this to all the hours until 11 o'clock in the evening. And okay, one notebook computer of 30 watt operating from 6 p.m. until 9 p.m. So from 6 p.m. 18 o'clock until 9, these 4 cells we need to add another 30 watt. So 30 watt means comma 0 3. So that means that I need to change this, add this cell with 0.03, so it means that it is 0.09. Okay, from 6 until 9, so I need to also add 0.03 here, so it means that 390 watt here, and this is the final cell, 390 watt. Okay, so yeah, yes, I'm correct. Okay, so afterwards the final load is one TV set of 100 watt operating from 8 p.m. until 10:30 p.m. So again, I don't have 10:30, I can enter it until 11 o'clock again. So 100 watts, so it needs 0.1 should be added to from 8 p.m. to the rest, so it is 0.490, then exactly 0.490, and then this one is 0.460, and the last one also 460 watt. Okay, so everything is also automatically copied to all the cells to the right and weekend, so I'm going to click OK. So this is how our load profile looks like for now, and this is the yearly profile. As we already know, until 9 o'clock or 10 o'clock nothing happens, it's completely zero. Then we have a slightly load around 60 watt, which is only for the ventilator, and then afterwards we have our peak here. So you can also see here that the average of these amounts are 2.86 kilowatt hours per day, and I also need to add this average in the baseline to the scale value here, 2.86. If I don't do this, I don't get any results, since HOMER considers this a scale value for an amount of load. But okay, I'm going to put it equal to baseline, so nothing is changing. Yeah, there's no efficiency for the load, nothing else. So let's go to see the plots, for example. Here, these are the monthly scaled monthly averages. We don't care about that. Profile here, exactly. So you can see that all the profiles in all months are exactly the same, but this is what our load profile looks. This D map is exactly the same as this one. Histogram is also like this, and then we go to the next part. So now we need to add our battery system. It says that calculate the battery size. Yes, okay, so I'm going to choose the battery. In the components, I can click on storage button here, and then I will choose to keep these generic 1 kilowatt hours lead acid battery as what it is right now. I can also choose lithium ion or other types of storage system, but let's go with this one. I'm going to add storage. Okay, so yeah, so the battery size, the battery system voltage should be 24 volts, so it means here it is 12 volts already, so I need to add a string of 2 batteries, so it means that 24 volts. And battery cycle efficiency is 8 or 80%. I can find the round trip efficiency of the battery here is 80%. This is not it's not possible to edit this number, but it is exactly by luck what we want. But you can choose other types of batteries, and then they also have different storage efficiency, but this one is good enough for us. Then let's go to efficiency of charge controller, and inverter efficiency is also given in the question, but I also need I need to edit these numbers in the parts, in the coming parts. So yeah, everything with the battery looks good enough for now. So let's add a PV system, our previous modules here. I'm going to exactly again keep generic flat plate photovoltaic modules. So I'm going to click on add PV, and I can see that the rating factor is by default 80%. Yeah, lifetime is 25 years. That is correct. Yeah, I need to enter the efficiency of the PV panel at 10%. So I'm going to click on advanced here, and then let's go to the temperature tab, and then I need to check this consider temperature effects check mark, and here efficiency of standard test conditions is by default on 13%, so I'm going to change it to 10% depending on what the question says. And in the question there's nothing about temperature coefficients or temperature effects on power, so I'm going to change it to 0 just to correspond our simulation to the exercise. And yeah, and about the charge controller, there is this efficiency of 95%, but we don't have charge controller in the components of the HOMER Pro. We have a controller which is something else, and we have a converter. Usually the charge controllers can be considered with the battery systems, but also in HOMER there is not this possibility to add this charge controller inside the storage system. But there are many devices. There are various MPPT controllers or MPPT trackers available now in the market that they have the MPPT function and also the charge controller function. So I'm going to consider this amount of efficiency in the maximum power point tracker. So here it says explicitly model maximum power point tracker. I'm going to tick this check mark, and then the efficiency is 95% by default, so it's what we need. And yeah, nothing else about the orientation. I just keep what the program suggests afterwards, and then I'm going to click on OK. Okay, so efficiency of the PV is also added. Next part is the efficiency of inverter. So as you can see, there is also 2 errors here. I need to add a converter or inverter since my load here is AC on AC side, of course, and PV and battery both are on this side, and I need to connect these two bus bars with a converter. Okay, so I'm going to click on the converter here. Yeah, there's system converter is already chosen already, so I'm just keeping it like that. And the inverter efficiency must be 90%. So I say inverter input efficiency here is 90%. And about the rectifier, I also put it 90%, but we don't use that much. And I guess that was it. Yes, let me see. You can also take a look at the question here. Okay, so yeah, that's it. Let's now continue. Okay, I need to also add the costs of the components to the system, so I'm going to click on PV panel for now. Let's change the unit to euros instead of dollars. So let's go to here in the project, and in economics you can choose euros. Okay, so let's go back to PV. Now all the units are in euros. PV panel including duties and taxes must be 1 euros per watt peak with lifetime of 25 years, which 25 years is already added here, and 1000 per kilowatt. Okay, here 1 kilowatt is 2500 is already added by default, which is too much for us. But I will also add the mounting and support structure cost, which is 50 cent per watt peak. I'm going to add 1500 euros for each kilowatt, and then for the replacement also the same price. And yeah, operating and operation and maintenance, I'm just keeping it as what it is now. Okay, the final part is to add the price for the battery systems and its lifetime. So I'm going back to our battery system, which is here, 1 kilowatt hours lithium acid battery. So lifetime here it is 10 years by default, but I'm going to change it to 4 years as what the question says. And the capital price for 1 kilowatt hours, which our capacity, nominal capacity is also 1 kilowatt hours. So it's 300 euros, which is the correct number. So I'm going to keep it and not changing anything else. Okay, so now we can maybe run the simulation. One more thing is the error here, define temperature for PV. Since we have chosen to consider temperature effects for the PV as well, the program also gives us this error, and we need to download the temperature data. But actually I have chosen temperature effects on power as 0%, so in the end there's no effect from the temperature, but let's download the data, so it will be, so that the error will be gone. So let's go to the resources and temperature, or let's click on the error itself, so it just guides us directly to this page. I'm going to click on download from internet, that's it. And you can see that in Rio de Janeiro the average temperature in January is 25, and then in our summertime or in their winter time it will be around 19. So yeah, that's it. So let's restart the simulation. So if I click on this calculate button here, the simulation will be happening. Now you can see these different cases, and then okay, so it automatically goes to this page. there is a summary page and table and graphs. I'm more comfortable with this view of the results. So it means that this line is one scenario, okay, and it is categorized, and this check mark for categorized is checked here. So if I click on overall, I can see many different scenarios, but all of them include PV, battery system, and an inverter. Okay, so I'm going back to categorize, because the categorize will choose the best one and then the cheapest one with all the through all the scenarios with same components. So this one is the cheapest one with consisting PV panels, storage system, and the inverter. But for example, if I had a grid also connected to the system, these options will be more, since the grid and the battery and the inverter can also be another option. The grid, PV, and battery could be also another option, and there are multiple options as well. So, but for now, we can see that there's only one option, and this is the cheapest one with these components. So, okay, the simulation tells us that we need 1.8 kilowatt of PV panels. It is 1,800 watt peak. And then this is the column for our battery. We need 14 batteries, each with nominal capacity of 1 kilowatt hours. Okay, this column of PV MPPT, it shows the results for the system with the maximum power point tracker. Of course, it helps us a lot. It helps us a lot, sorry. It means that instead of 1,800 watt, we need only 1,000 watt of PV modules. And it's a really good saving. And as I said, yeah, 14 batteries of 1 kilowatt hours is needed. The converter of 813 watt is needed. This NPC is a net present cost, and it is equal to the costs of the whole system for the whole period of its lifetime, if we want to pay all the costs in the beginning of the installation. Okay, so and this all the scenarios are sorted according to net present cost. So if I click on overall here once again, I can see that yeah, this NPC is going higher and higher for other cases, but of course with categorized view it shows the best one and cheapest one. COE is cost of energy. It is a cost of unit of energy. For example, in this case, for every kilowatt hours, we need to pay 1.54 cents, 1 euros and 54 cents, which is really expensive considering that we can buy the electricity from our grid with numbers around 25, 28 cents. Okay, but now if we want to limit ourselves only to PV energy and the battery systems, the system costs 1.54 cents for every kilowatt hours. There are other columns as well and other informations, of course, like operating costs with unit of euros per year. Renewable fraction, of course, it is 100% since we don't have any conventional energy sources. Then we have the capital cost, production, kilowatt hours per year, autonomy of the battery systems, which is 70 hours. It's around 3 days. This is days of autonomy. And the thing is that in HOMER we cannot define, we cannot enter this days of autonomy on our own wheel, but the program suggests it on its own after running the simulation. And yeah, that's it. But if we double click on this case, so it will go to another window and shows us more information. So the first one is about the financial aspects of our project. This is net present cost. The most cost of the system is going to be dedicated to the battery systems. Here, generic 1 kilowatt hours lead acid battery is the highest, has the highest price through our whole system, and then the PV modules, and then finally the system converter. Yeah, there are other financial and economical tabs here. I'm going to click on this electrical one more time, and then see that the production of flat plate PV is 2,200 kilowatt hours per year, and it was 100% of the whole production in this system. There is no other energy resources, and yeah, exactly, renewable fraction is also 100%, and then this is the share of PV production through the whole year. In August was this much, in March was this much, and for example in January was also around 0.17 megawatt hours. And if there was other energy sources, so here this table, this diagram was also divided into different energy sources as well. I'm going to try it soon one more time. Renewable penetration is another part, so you can see that in these diagram you can see the penetration of renewable energy through the whole year by various parameters. And then if I go to the generic 1 kilowatt hours lead acid tab, it shows me different information about our battery system. So as we said, 14 batteries, we need 2 batteries in each string to have the 24 volts. Then 7 strings in parallel we need. Days of autonomy is around 3 days or 70 hours. Nominal capacity, these are the stuff that we don't care about that much right now. The frequency of the state of charge of the battery is also like this. So it says that most of the time the battery is charged until, it has the capacity of 76%, and as we wanted, it doesn't go less than an amount of 54%. I guess in the simulation was 40% as minimum state of charge, but we can see that in real simulation it didn't even go less than 58 or something percent. And then you can also see the state of charge of the battery through the whole year and through the hours of each day. You can see that in the hours in the evening the battery is almost full all the time, and then in the mornings the battery is half empty, or is 77%, for example. In this case, it means that during the day, which the irradiance was good enough, the battery was getting charged, and then in the evening, starting from 12 o'clock or until 18 o'clock, the battery is almost fully charged. Okay, the next tab is about our PV modules. You can see that the PV power output is also illustrated in this diagram for all days of the year and then all hours of each day. And you can see that exactly based on the input data for Rio de Janeiro as the input irradiance data. So you can see that only between these 2 hours we have irradiance, and these are the times that our PV modules had some outputs. Next tab is about our inverter. So you can see that this This is the inverter output, and this is the rectifier output. Since we are always working with the conversion of DC electricity to AC, so we can only see this diagram for inverter. Yeah, and for rectifier there's nothing. And final one, if we go to the emissions, since we had only renewable energy sources, we don't have also any emissions. So carbon dioxide, carbon monoxide, sulfur dioxide, and all the harmful emissions are set to 0. Okay, so now for the second part of the exercise, I'm going to change our numbers for the load only for those lights of 300 watts from 7 p.m. until 11 p.m. and I will substitute them with 40 watts since we have 5 LED lights of each 8 watt. So I need to go to the load part again here, and then I will open the show all months here, and by changing our conventional lights with LED lamps, I need to reduce our load from 7 p.m. until 11 p.m. with the amount of 260 watt. Okay, so I'm going to find 7 p.m. until 11 p.m., which is from this cell and till the final cell, and then reduce these for 260 watts. So this one will be 130 watt, this will be 230, then again 230, then this one will be 200 watt, and this one also needs to be reduced by 260 watts, so it is again 200 watts. Okay, and yeah, so all the new values are updated through the whole year. So I'm going to click on OK. I can see that the load profile has also changed, and I can see a sign here which model does not match results, and I need to recalculate my simulation. So I'm going to rerun the calculations. Okay, we can see that there is a new case here. The numbers are changed, so we're going to briefly just compare them. So first of all, in the older case with the normal lamps or conventional lamps, the PV modules were about 1.8 kilowatt, and now they are at 1.91 kilowatt. Okay, this is strange because we have reduced our load, but the PV is simulated as a higher number. And for PV with MPPT, it's again still on 1000 watt. Yeah, before was also like this, but the battery in the older system was 14 battery systems, and now it is 12 kilowatt hours. So 2 of the batteries are gone, and batteries are really costly, so it means that our system should be a bit cheaper. Okay, then let's go to the NPC, net present cost, and our older number was I have written it here, 21,000 almost to 20,700 euros, and now it is 18,400. So it means that around 2,000 euros or around 3,000 euros is less now. And then cost of energy for every kilowatt is reduced from 1.54 euros to 1.37 euros. Okay, so this is the amount of saving that we saw through HOMER about the costs. Yeah, amount of loads, as in the exercise also says, the amount of load is 86% less than before, but the amount in the cost of the system after the simulation in HOMER, it is much less than this amount. Just to show you another small example, I'm going to add, for example, a grid to the system, so the system is not off grid anymore, it is also connected to the grid. And then grid power price is 10% here, so I'm going to change it to 20, for example, which is more realistic. And then if I can sell back our extra electricity to the grid of around, for example, 10 cents. So this is a normal grid. I need to calculate the system once more. This time I expect to have 2 rows of results. Yeah, we need to wait a bit. Okay, I have even 4. So let's see. As I said, the view is categorized here, so each line has a system with different unique components. Okay, not any of these 2 lines have exactly the same components, but if I click on overall, this will change and all the cases with different components will be shown. So I'm going to choose categorize once more to see the cheapest scenarios. So the cheapest scenario is the first line right now with a PV module and connected to the grid with no battery system, and also an inverter that we need. So the PV panel in this example will be 290 watt, which of course is maybe 1 or 2 modules, so it's not much, but it's just to have some renewable energy in the system. And you can see that there's no battery, 0, and let's go to the net present cost, and the costs are 2,500 euros. In our previous examples it was around 18,000 or 20,000. Okay, so and also you can say that the cost of energy is around 16.7 euros, 16.7 cents per kilowatt hours. And if I open on this scenario, I can see that, for example, in this case, electrical, I can see the share for the production of each of our sources for each month. Of course, the grid was had the main share of the production, and PV had the smaller one. And then renewable penetration, you can see that, okay, what happened and at what times of the year we had some production from our PV panel. And then you can see also in this diagram, of course, the PV panels had a low amount of production since there was only 290 watts, and that's it. So the second option is the option only with just the grid, nothing else, no renewable, no other stuff. So you can see that, yeah, as we entered 20% for each kilowatt hours, that cost stays the same. And but through the 25 years we need to pay this amount of net present cost for the whole system, for the feeding of the whole system and our loads. Another case is with all components, as we talked before. Yeah, but this time the PV is also a low number, and the price of COE, the cost of energy, is 33 cents, and it's still too high. And the final option is with the grid and storage system and no PV. And this means that yeah, this is also the worst case, or the highest has the highest price in these examples. You can see that the cost of energy is 38.5 cents per kilowatt hours, which is too much. Okay, so yeah, as I said, you can play with all the components. You can add wind turbines as well. You can do whatever you want, generators, and you can continue playing with the software and get interesting results. But the target of this tutorial was to get you familiar with this software. There are various softwares that are doing almost the same things as Homer does, but Homer is um, a really good and professional software for this matter, and I hope you have learned something for it. Thank you for your attention, and I wish you good luck.